Chapter 9.2, well, the second half is Euler's method. Now, what does Euler's method do? Euler's method basically uses a differential equation in order to find an approximation given an initial starting point. So what do I mean? Well, in this differential equation, do we really know what y is? What does y look like? In this case, we can't actually solve for it. Therefore, we can do things like maybe find the slope field, right? And we can find some sort of an approximation of what y might look like. Like, for example, I have to be given an initial point. So, for example, if I go through the point 0, 1, I can pretty much find an approximation to what it looks like. 0, 1, like right there. We know that the slope is 1. It'll get steeper and steeper. It'll plateau maybe to a -1 over on this end. The curve looks something like this. Now, what I'm doing with that curve, what I'm doing with Euler's method, is I'm finding a linearization model. So I'm starting at 0, 1, and I'm going to find a linearization model at 0, 1. And I'm going to use that to approximate the next step. So if my change of x, they'll tell you what your change of x should be. So let's say my delta x is 0.1. So my first step is to find L of x at 0, 1. Now L of x is going to be, it's y1, which is 1, plus the slope at 0, 1, the instantaneous slope at 0, 1, so in this case it'll be 0 plus 1, which is 1, times x minus x1, which is 0 here, right? And I'm going to use that in order to approximate 0.1. So in this case, this is my slope. This is my equation, 1 plus x. So right here, a good linearization model is maybe 1 plus x. Now what I'm going to do next is I'm going to find 0.1. I'm going to plug in 0.1 into this blue linearization model in order to find the output at that point. So this will give me 1 plus 0.1, which is 1.1. Right? So right here at 0.1, 1.1, I'm going to use that to find my next L of x. So I'm going to find L of x at, this time, 0.1 and 1.1. Now what that's going to give me, one more time, is going to be my y1 plus the slope, instantaneous slope, using the slope field, using the differential at this point. So that'll be x plus y. So 0.1 plus 1.1, which gives me 1.2 times x minus x1. Right? Now this equation of a line has a slope of 1.1, a y point of 0.1, 1.1. 0.1, 1.1 was right here on this blue line. My slope is a little bit steeper. It's going to follow the curve, but it's not quite the red curve. Right? So what I'm going to do is I'm going to find the next x step, which is going to be here at 0.2, plug it into the green linearization model. So I'm going to find L of 0.2 this time. And instead of plugging into the blue model, I'm now going to plug it into the green model. So this will give me 1.1 plus 1.2 times 0.2 minus 0.1, which is just 0.1. This will give me 1.22. So again, when I plug in 0.2 into the green model, my output here is 1.22, this point right here. So then what I'm going to do next is I'm going to find a linearization model at 0.2, 1.22. Okay, so if that's the case, again, I'm going to use my point slope form, which is going to be y1 plus the slope, the instantaneous slope at this point, which again was defined by my differential, x plus y, So x plus y will give me 1.42 times x minus x1, which is 0.2. Now that purple, this equation of a line, is my next linear approximation. My slope is getting a little bit steeper, 1.42. Starting from this point, it's going up a little bit steeper now, right? So I'm going to use that and plug in my next step, my next point, which is 0.3. So I'm going to find the linearization at 0.3. So 1.22 plus 1.42. If you notice, every single time we move a change of x of 0.1, this difference remains 0.1. So 0.3 minus 0.2 is 0.1. Now this will give me 1.362. So my next step, again, I'm going to repeat. And basically what the problem will ask you to do, it'll ask you to approximate a certain value. For example, f of 0.5, right? So what I'm doing is I'm using the differential and I'm approximating I'm given a step size of 0.1 and I'm using that to approximate f of 0.5. So right now we've gotten up to approximating 0.3. All I have to do in order to get up to approximating 0.5 is do it a couple more times. So you can find the next linearization model at 0.3, right, which is this equation, plug in 0.4. Oh, there's my final answer. That's after you plug in, you do it one more time, find the linearization at 0.4, and then plug in 0.5. So your final approximation is going to be this value right here. It's going to be a good approximation for 0.5 as the input. So that curve is going to be up here somewhere when I plug in 0.5. Right? It follows the curve somewhat, so it'll be pretty accurate to that red output right there. So in this case, the smaller the step size, right, the more accurate it will be. So if I jump all the way to 0.5 and try to approximate f of 5, right, the more further off from the original red curve will become. So that is using Euler's method.